So, good evening, everyone. Welcome to the eighth live session for the course Concrete Technology offered by NPTEL. I am Arshit Agrawal, a PMR scholar from the Department of Civil Engineering, IIT Bombay, and I will be taking weekly live session for this course for the entire course duration. So, in today's session, we'll first revisit the last live session, just a quick recap to whatever we have discussed, and then we'll go through the week 8 content of the course. So, week 8 content discussed about strength of concrete, mostly focusing on the compressive strength and a little bit on the tensile strength of concrete. So, for this, the session is divided into following sections. First, we will have a basic overview of strength of concrete. Then we'll discuss in detail about compressive strength of concrete, theories of crack and pores that governs the compressive strength failure in concrete. Then we'll talk about how cement paste aggregate bond and aggregate properties affect the compressive strength of concrete. We'll talk about how testing setup and the sample dimensions they affect the compressive strength, and finally we'll discuss about tensile strength of concrete. So in between, I will have some objective questions. In total, there will be around say, 15, 16 questions that will challenge your understanding of the concept. And finally, we'll conclude the discussion and I will try to address any other queries post discussion. So last week we concluded the seventh week for of the course where we talked about post mixing operations on concrete. In post mixing operations, we have transportation, pumping, compaction, and curing of concrete. When transportation and mixing are done together, it is known as ready mix concrete. For ready mix concrete, we talked about agitator trucks and different types of RMCs like transit mixed, shrink mixed, and central mixed, and their application areas. After ready mixed concrete, we talked about different ways of transportation for conventional concretes, which includes transportation using wheelbarrow, mortar pan, bucket and ropeways, conveyor belt, transit mixer, and pumpings. Before moving into pumping, we talked about workability of fresh concrete and different components of workability and different methods for measuring workability like slump value, compacting factor test, flow table test, and VB consistometer test. We saw how each of these testing work and their application in different concretes based on the workability of concrete. We then talked about different types of pumping system like boom and truck mounted pump, trailer mounted pump, and high pressure trailer pump. And in trailer pump, we talked about single piston and double piston pump. After pumping, uh, after pumping the concrete inside the formwork, we talked about compaction methods, in which first was manual method, which includes rodding, ramping, and tamping, and then mechanical methods, which includes internal vibrators, external vibrators or foam vibrators, surface vibrators, and vibrating table. We also had a little bit discussion on underwater concreting, where compaction can't be done. After compaction, we came to curing, which can be done during using immersion ponding, spraying and fogging, or wet covering. So all these are water-based curing, which may not be effective in hot and humid condition where there is high evaporation rate. So in such humid condition, we have membrane curing using plastic sheets or water repellent chemicals, uh, bituminous emulsions, and plastic sheetings. So we discussed about early strength concrete, where we need early strength gain. We talked about steam curing as a mean for early strength gain in concrete. Okay, so this was all from the last session. Any doubts in the any discussion of from the last session? Okay, so we will move ahead then. Now, once we have designed the concrete and poured the concrete inside the formwork for a specific structural element, the next thing that matters to us is the hardened properties of concrete. And in hardened properties, the most important property from engineering point of view is the strength of concrete. So strength refers to the ability of concrete to resist force without breaking or deforming. Okay. Now, a concrete element can exhibit different types of strength based on the direction of force applied at the structural element and the interface. Okay, so these different types of strength are classified into four main categories. So we have compressive strength, which is resistance against axial compression. Suppose this is my concrete block, so this is known as compression force when I'm compressing the concrete. So that will give me the compressive strength of concrete. Then there is tensile strength, resistance to axial tension. So this is the pull out force. Okay, when I'm pulling a concrete block, so that will be a tension force. Then there is flexural force, resistance to bending forces. So suppose I have a reinforced concrete beam which is subjected to some bending moment, okay, or some central load or some uniformly distributed load, so this beam will tend to bend. Okay, so what is the flexural strength of the concrete? That is the resistance to this bending force that is applied on the concrete. And then there is bond strength, which is the adhesion between the reinforcement and concrete. So when we talk about reinforced concrete, this is my concrete and this is my reinforcement. So what is the bond strength between this reinforcement and concrete? That is also a very important force when we talk about strength of concrete. So, for all these types of strength, one thing is common. Strength, it determines the load carrying capacity of a concrete structure. So, in a simplest of manner, if we try to describe each of these strength, so high compressive strength ensures longevity and safety. Okay, higher is the compressive strength, better will be my concrete resistance to external forces. Then tensile and flexural strength are critical in applications like beam slabs and bridges, because here there are chances of bending stresses which can generate in concrete. Bond strength affects the interface between concrete and reinforcement, ensuring composite action in reinforced concrete. So when we talk about bond strength, it defines the interface between concrete and reinforcement, and it determines how resistive the concrete will be against the pull, if pull is applied on the reinforcement. Now, for concrete, we all know that concrete is strong in compression and weak in tension. But why is that so? So the answer to the statement can be given based on two theories. The first is the cement paste theory, that is based on the CSH bonding. So this we have talked in the first live session also. The strength of concrete, it comes from the dense matrix and the strong cement, say, calcium silica hydrate gel, which is the primary hydration product of cement hydration. So initially when we talked about concrete and its component, we talked about binders. Okay, and in binder we have cement. Okay, so cement, it reacts with water and it forms certain hydration products. So what these hydration products do, they bind the aggregate skeleton together and they provide the denseness to the concrete. Okay, and in hydration product, the main hydration product which contributes to the strength of concrete is the CSH. Okay, so CSH, it forms the dense interlocking network which binds the aggregate together. Now when we look at the structure of CSH, so it has a layered structure. Okay, there are different layers. Okay, inside each layer there is strong covalent bond which exists between calcium and silica and water. Okay, so within layer there are strong covalent bonds. Okay, and between one layer and two layer there is weak van der Waal bonds which hold two layer together. Okay, so when we apply compressive force on concrete, so what happens? This strong interlaminar force within layer forces, the bond, interlaminar bond, they resist the crushing against compression. However, when tensile force is applied on concrete, so this weak van der Waal forces acting against those tensile forces, and these weak van der Waal forces, they allow easy separation of layers. Okay, cause and which leads to failure in concrete. Okay, so that's why we say concrete is strong in compression and weak in tension, because of the strong covalent bond between within layers and weak van der Waal bonds between layers. Now, the second and the most commonly accepted theory behind high compressive strength of concrete is the concrete cracking theory. Okay, so in the simplest of manner for everyone to remember, the base behind this theory is to remember this one statement: a single crack inside concrete can lead to failure in tension, but multiple cracks are needed to combine to produce a failure in compression. Okay, so this is a very important statement when we talk about crack theory of concrete. How? So we know concrete is a heterogeneous material made of aggregate, cement paste, and pores. Now, due to different shrinkage and stress distributions inside concrete, there can be microcracks that can naturally exist in within concrete before any load is applied. Okay, so what happens to these cracks when some loading is applied? So if we see the crack behavior in tension, so when some tensile forces is applied on concrete, so what will happen, these micro cracks, they will start to open up. Okay, and as the tensile load increases, these crack will propagate rapidly and they will connect and they will cause brittle failure of concrete. However, when we talk about compression force acting on concrete, so what happens under compressive load, these cracks which are already present in the concrete, they are pushed together. Okay, instead of opening up, they are pushed together. Also, there is friction between cement paste and aggregate that will raise the crack growth. And even if the crack initiates, they tend to branch and form a tortuous path which consumes more energy and delay failure. So when we talk about concrete, suppose there is a crack here. Now, for the failure to occur, this crack need to propagate throughout the concrete. Okay, but what happens? There is aggregate distribution which is heterogeneous inside the concrete. So this crack, it can't go through the aggregate. It will go from the interface of cement and aggregates. So this path formation, it is not straight. Okay, it is branched, and this growing of this crack, it will take more energy and more time under compression load. Okay, so that's why compressive strength is usually higher in concrete compared to the tensile strength, because in compression multiple cracks needs to connect together to lead to produce ultimate failure in compression. However, in tension, a single crack can open up and cause failure in tension. Okay, now if we try to understand the nature of this crack from microstructure level, so there are three components in a concrete system. Okay, there is aggregate skeleton, there's cement matrix, and there is interfacial transition zone. Okay, so inside concrete, the crack propagation occurs through this ITZ. Okay, and you can see how this crack will appear. So this is my crack, and it is passing through the interface between aggregate and cement. Okay, so ITZ is basically the interface. This is my cement paste and this is my aggregate. So this interface between cement paste and aggregate is known as ITZ. Okay, and crack propagation inside concrete, it occurs through ITZ. Okay, however, outside concrete, you can see the failure is different. Okay, so uh, in the further slides we'll talk about why, how itz is weaker, how different properties inside concrete affects the compressive failure in concrete, and how different properties of outside concrete affects the failure pattern in concrete. Okay, so to understand both of these things, we need to relate the compressive strength to the cracks and pores that are present inside concrete. Okay, so first, we'll talk about how crack is related to the compressive strength in concrete. So there is a theory that is given by Griffiths, okay, which relates the failure stress of a brittle material. Concrete is a kind of brittle material, okay, and how failure stress is related to the presence of crack. Okay, so this researcher, the scientist, gave an equation to relate failure stress of brittle material, how and how it is governed by stress. So this equation says that sigma t is inversely proportional to the presence of initial crack length inside a material. Okay. Sigma t is equal to under root of 2e gamma upon pi into a. So sigma t is the tensile strength of concrete, or we can say compressive strength also of concrete. Okay. E is the elastic modulus of concrete, gamma is the surface energy, and A is the initial crack length inside concrete. So if we see here, higher is the crack length inside concrete, lower will be the strength of concrete. Now, the presence of crack tip, it amplifies the stress, meaning that even a small crack can cause significant failure under tension load, tension stress, and under tensile stress, because a small crack, it continuously amplifies when a tensile load is applied. However, in compression, the stress concentration is less significant due to crack closing effect and internal friction. So as we discussed few slides back, in compression, the crack, rather than opening up, it tends to close down initially, and then it slowly propagates, it connects with other cracks, and then ultimate failure occurs. And that too is resisted by internal friction and tortuous nature of the path of crack propagation. Okay, so that's why stress concentration is less significant, okay, in case of compression. However, in tension, the presence of a crack, it amplifies the failure. Okay, so this figure also tries to explain the same thing. Okay, we have energy on y-axis and we have crack length on x-axis. So in compression, you can see multiple crack. They combine to achieve sufficient strength which is required for concrete cracking. Okay, suppose I mark this is the strength that is required for concrete cracking. So multiple crack, they need to combine together to produce required energy for failure in compression. Okay. Now, when we talk about this crack merging effect in compressive load, so how this crack merging occurs? Okay, so for this there is simple stage-wise explanation of how crack propagation occurs inside concrete in compression. Okay, so when we talk about concrete under compression, the cracks form a fracture process zone. Okay, there is a thing known as fracture process zone. Okay, this is formed before complete failure of concrete. Okay, so what is this fracture process zone? So that is divided into different stages of crack propagation. So stage one is the micro crack initiation. So we have said that due to heterogeneous nature of concrete and due to shrinkage and different properties of different materials that are used in concrete naturally contains micro cracks, okay, inside it. And these micro cracks, they are not active at low stress level and they don't significantly affect the strength of concrete. Okay, however, when we apply compression load on concrete, okay, when we apply load, so at 50 to 70% of the ultimate load, suppose we know that the compressive strength of concrete is 50 MPa. Okay, so what will happen when this compression load will be 25 to 30 MPa? So at that 50 to 70% of the ultimate strength, what will happen as compressive strength increases, compressive stress on concrete increases, the micro cracks that are there inside the concrete, they start to become active. Initially they were dormant, they were not propagating, they were there, they were existing, but they were not propagating inside concrete. Now they will activate. Okay, the cracks, they won't propagate rapidly, but they will rather accumulate and interact. Okay, so this crack propagation, it won't happen rapidly, as rapid as it happens in tensile loading. Rather, it will slowly propagate and it will connect with each other. Okay, multiple cracks, they will connect and they will accumulate with each other. Okay, and they are distributed due to bridging effect of aggregate. So we have seen due to aggregate, the crack propagation is not straight, they will be distributed as it passes to the ITZ between cement paste and aggregate. Okay, so that will happen at 50 to 70% of the load. Now at 70 to 90% of the strength, so for 50 MPa, it will be like in the bracket of 35 to 45 MPa. So when this much load is applied on concrete, so what will happen, the cracks that are micro cracks, they will start to connect and they will form a larger fracture plane. So okay, so this micro cracks that are existing inside concrete, they are connecting with each other, and now they will tend to move towards a macro crack. Okay, a larger crack. Okay, that will start to form. And finally, when we apply the remaining 45 MP to 50 MP load, these macro crack, they will fully connect, and they will lead to shear or explosive crushing failure of concrete. Okay, so this is known as the fracture process zone. Initially we have micro cracks which are dormant, which are not active, are at about 50 to 70% strength. The micro cracks, they start to connect with each other, they pass through the ITZ and they interact and they grow. At 70 to 90%, the micro cracks they bridge enough to become a macro crack, and at 90 to 100%, this macro crack it fully connects throughout the concrete, and it leads to shear or explosive failure, crushing failure of concrete. Okay, so this is how crack is related to the strength of concrete. Now, how pores inside concrete influence the strength? So when we have when initially we talked about a concrete mixture design, we know there is cement, there is water, there is aggregate. Okay, and there will be admixtures. Okay, when we mix all these components, we make concrete. But naturally there can be pores also which are inside concrete. There may be entrapped air voids, or there may be capillary small capillary voids or gel pores that are existing inside concrete. As water interacts with cement paste to form hydration product, it can lead to some pores that are left inside concrete. Okay, so how this porosity inside concrete affects the strength? So there is a theory, Power's law, which expresses the relationship between porosity and strength, and it says that the compressive strength of concrete, it is 8 a into 1 minus p to the power n, and p is the porosity. Okay, so it says that compressive strength is inversely proportional to the porosity. So more is the porosity, lower will be the compressive strength of concrete. Okay. Now, if we combine this Power's law with Griffith's theory of crack initial length, we can see that the stress capacity of a material, it is inversely proportional to the porosity inside the concrete, and it is also inversely proportional to the initial crack length inside concrete. Okay, so this is how compressive strength is related both to the porosity and the strength of the cracking inside the concrete. So higher porosity reduces the strength, and this is clear from this 1 minus p indicator. So as porosity increases, the effective strength decreases proportionally, and strength is inversely proportional to rm. Rm is the crack initial crack size, or the pore radius inside the concrete. Okay, so it follows the fracture process zone as we have discussed earlier, where material strength is reduced due to micro crack and flaw size, and larger pores or crack leads to lower strength, and which is consistent with the Griffith's failure theory in brittle material. Now, next question. So we have understood both how pores is affecting the concrete strength and how cracks are affecting the concrete strength. But one thing that is still not clear, why crack passes through ITZ. Okay, so we have cement paste, we have aggregate, and we have the interface between cement paste and aggregate. So why crack is passing through the interface? Why not it is passing through aggregates, or why not it is passing through the cement paste? So apart from conventional pores that are there in concrete like gel pores, capillary pores, and macro pores, there are additional pores also which are present in concrete at the ITZ. Okay, and why these additional pores exist as ITZ? Due to wall effect. So we have aggregate surface here, and we have cement paste here. Okay, so my cement paste, it may not be completely surrounding the aggregates, or we have two aggregates which are interacting with each other. Now these aggregates, they may leave a small void in between, okay, which will be treated as a pore. So this is known as wall effect. Then there is one-sided hydration growth. So aggregates is inert material, it won't interact with water, but cement paste is undergoing hydration. As hydration goes on, cement paste volume will shrink, which can bring some porosity at the interface. Then there are shrinkage. Okay, due to loss of moisture, there can be shrinkage which can bring porosity at the interface, and there is trapping of bleeding water. So if we add too much water, then that water, it will appear at the interface between aggregate and cement, and upon evaporation of this water, it will again lead to porosity at the interface. So apart from these conventional pore, there are a lot of additional pores that can exist inside the concrete, and all these additional pores, they exist at the ITZ. Okay, so we say that ITZ porosity is more, and the pore size are larger compared to the pores which are present between cement paste in a concrete, and thus the strength of concrete is governed by the ITZ. Okay, because it has more pores at the interface, and we have seen that porosity is directly related to the strength. Higher is the porosity, lower is the strength. Okay, so up to 70% of ultimate load cracking is generally due to ITZ cracking. Okay, so whatever crack growth we see inside concrete, up to 70% of that crack growth is due to the ITZ cracks which are present inside the concrete. Okay, so you can see this relationship from here also. As W by C ratio increases, the porosity inside concrete increases. Okay, and with this porosity increase, there will be porosity at the ITZ interface also, which is increasing, and that's why the strength of concrete continuously decreases. So we have seen this figure when we talked about design of concrete based on ACI method. Okay, so this is how pores, cracks, and ITZ it affects the strength of concrete. Now, just try to answer some questions regarding compressive strength. And in the meantime, if anyone has any doubt regarding any concept that we have discussed, you can ask. Just think about what will be the answer for question number one. Which of the following is the reason behind presence of naturally occurring cracks in concrete? And if anyone has any doubt regarding whatever theories that we have discussed regarding compressive strength or any confusion about compressive strength of concrete, you can freely ask. Like you can you can type in the chat box or you can unmute and speak also. If there are no doubts, just try to answer these questions as quickly as possible. So, what will be the answer for question number one? Which of the following is the reason behind presence of naturally occurring cracks in concrete? Can anyone tell me? Just think it is a very simple question, and we have already discussed about this question in the theory. Yes, the correct answer is D. Okay, so we have seen the cracking inside concrete, it occurs naturally. Okay, and what can be the reason? Shrinkage. Okay, so due to hydration of cement, we have seen it is an autogeneous shrinkage which exists because cement hydration has lower volume compared to cement and water separate. Okay, so that can bring shrinkage. Evaporation of water from concrete can lead to shrinkage. Cracks inside concrete, and those cracks will occur naturally before any load is applied. Then thermal expansion difference is there between cement and aggregate, which can lead to some cracking. ITZ weakness that we have seen, there are multiple reasons due to which there is cracking at the ITZ: the wall effect, the one directional hydration effect, the shrinkage effect, the bleeding water effect. All those can bring cracks inside concrete even before any load is applied. Question number two: according to Griffith's fracture theory, how does an increase in microcrack size affects the tensile strength of concrete? Okay, so we have seen the theory and how crack is related to the strength. Okay, based on that theory, can anyone tell me what is the correct answer for question number two? Any answers for question number two? ITZ weakness means the presence of pores at the ITZ. Okay, more is the porosity, lower is the strength of concrete. So we say ITZ is the weakest link in a concrete because it has more pores. Okay, and through pores the crack can easily propagate. So we have seen when we talked about how crack propagates. Okay, when crack grows, aggregates they tend to hinder the crack growth. It makes the crack propagation tortuous in nature. Okay, however, if there are pores, then crack can easily pass through them. Okay, so ITZ it has more pores, so that's why cracking happens through ITZ because it is weak inside concrete. Yes, the correct answer is B. So we have seen the relationship between crack length and strength. Okay, strength of a concrete it is inversely proportional to the crack tip. Okay, so the Griffith theories it states that stress concentration at crack tip is proportional to the crack size, and larger crack can cause stress amplification. So if there is larger crack, then under tensile load there will be amplification of stress that is acting inside the concrete, which can lead to early failure in tension. Question number three. In concrete under compressive load, which failure mode dominates after the formation of fracture process zone? So once the fracture process zone has formed, the micro cracks has started growing, connecting, linking to form a macro crack. Then what is the failure pattern? How concrete fail under compression? Can anyone tell me? Okay, yes, the failure is shear failure and aggregate crushing. So when we talk about failure under compression, there is shear failure due to slipping of planes when a crack is formed, and it is followed by crushing of aggregate. So once there is cement ITZ collapse has happened, then upon further load, aggregate crushing can also happen. Suppose I am using lightweight aggregates inside concrete and aggregate strength is lower compared to the strength of ITZ or cement paste. So in those cases, aggregate crushing can also bring ITZ failure. It is not necessary that crack will pass through ITZ only. It can pass through aggregate also if aggregates are weak. Okay, so that's why aggregate crushing is also one of the ways in which failure can occur inside in concrete under compressive load. Then answer these two more questions. Which type of pores in cement contributes most significantly to the reduction in strength? So can anyone tell me the answer? The correct answer will be entry in air voids. Okay, so if you remember the in week session 1 or session 2, we talked about how different pore size they line up based on their size. Okay, how different pores line up based on their size. So these entry and air voids they are much larger in size compared to capillary pore or ITZ voids. Okay, so if there we have more entry in air voids inside concrete, we have much larger voids inside concrete. Then those voids they will very easily connect micro crack together and bring failure of concrete. Okay, so compared to all types of porosity, the entry in air voids are the largest, and larger is the air void, lower is the larger is the pore inside concrete, lower will be the strength inside strength of concrete. Okay, it is about the size of pores. Okay, and entrained air voids they occupy much more volume inside concrete compared to any other pores. And that's why when we talk about use of air in training admixture, we say it brings one disadvantage. Though it is improving the freeze and thaw resistance of concrete, but it will also significantly decrease the strength of concrete. Okay. Question number 5. How does fiber reinforcement improve the strength of concrete based on crack theory? So you would have seen or you would have heard sometimes we add steel fiber, plastic fiber, glass fiber inside concrete. And we say this concrete is fiber reinforced concrete. So how they improve the strength of concrete? What fibers are doing inside concrete? Yes, the correct answer is B. So when we talk about concrete, there are micro cracks that are present inside concrete. Suppose this is a concrete and this is a micro crack which is present. So what will happen when fibers are there inside concrete? The fibers they bridge the micro cracks and they delay the propagation of crack, especially under tensile loading. So we have seen that in tension or in flexural loading, a single crack is enough to amplify and feel the concrete. Okay, however, if fibers are there, what will happen? These fiber, it won't allow crack to open up easily because it is bridging the crack. One end of the fiber is in cement paste, the other end of the fiber is in cement paste, and it is passing through crack, okay, which is present inside concrete. So it will tie the crack rather than, and it won't allow crack to easily open up. Okay, so that's why it improves the strength of concrete. Okay, so I hope everyone are clear with the theory of how pores and how cracks they affect the strength of concrete. Now, from our understanding of pores and cracks, if we try to summarize the effect of cement paste on strength, then we can see the following flow chart. Okay, so first is the type of cement. Okay, uh, a slow strength gain cement, there are slow strength gain cement, there are rapid hardening cement. Okay, so this type of cement, it will dictate the formation of csh, okay, at the rate at which csh is formed, and that will dictate how dense my concrete is and how well my aggregates are binded together. Okay, that can dictate the strength of my cement paste and eventually the strength of concrete. Then the age of cement paste. Okay, with age we have seen that cement paste it densifies and hydration proceeds. Okay, then curing condition, so which we saw in the last session or few sessions back, that air in the last session itself, yes, that air curing it results in slow strength gain because there is evaporation loss from concrete. However, moist curing it results in faster strength gain because there is no evaporation loss from concrete. Then admixtures used, okay, like mineral admixture, if we use, they can delay or increase the strength gain based on reactivity. Okay, so these four basic parameters of cement paste system, they affect the degree of hydration and the gel structure and composition. Okay, so when we talk about these effects, they are affecting the degree of hydration of my cement paste or the composition or structure of my cement paste. Okay, now higher is the degree of hydration, denser is the paste, then higher is the strength of concrete. While a compact gel structure has low porosity and it has more strength. Okay, now W by C ratio of cement paste and the degree of hydration of cement paste, it directly governs the porosity of my paste system, and this ultimately affects the strength of paste, or we can say strength of concrete. Okay, so porosity and gel composition, they together affects the strength of concrete. Okay, now, so the cement paste part mainly accounts for the initial porosity and crack. Like at the age of testing, when load is applied to concrete, the crack doesn't propagate through cement, it passes through the paste aggregate boundary. And thus, what is now important for us to understand is what is the effect of that paste aggregate boundary and how it can influence the strength of concrete. Okay, so this was all about how cement paste affects the strength of concrete. Now we'll go further, we understand how the paste aggregate boundary affects the strength of concrete. Okay, so if we see this figure here, there are three curves for strength versus cement paste which has been shown. Okay, curve 1 is the strength of paste. Okay, curve 2 is the strength of paste aggregate bond, and curve 3 is the ratio of bond to paste strength. Okay, so one thing we can observe from the pattern that we can see here is that the paste strength and the aggregate paste aggregate bond strength, they don't always follow the same behavior. Okay, some it is decreasing, it is decreasing, so but sometime it may happen that the cement paste strength is decreasing but the paste aggregate bond strength is increasing. Okay, so that's why we say it don't always follow the same pattern. Okay, so we can say that it is not just the paste strength that governs the paste aggregate bond, but there are some additional factors also which are associated with the aggregate surface that can play a role at the that can play the role in the paste aggregate bond strength. Okay, and this gives rise to two questions that we need to understand: how aggregate is affecting the paste aggregate bond, and how this effect of aggregate contribute to the property of ITZ. Okay, so let's try to answer these two questions. Okay, so we have seen the effect of cement paste, and we know that crack propagates through paste aggregate bond. But from this figure we got to know that it is not just the cement paste that governs the strength of a paste aggregate bond. The aggregate properties can also influence the strength of a paste aggregate bond. So we need to see what how aggregate properties are affecting the bond strength. Okay, so if we talk about different factors that affects the paste aggregate bond strength, there are three main factors which influence this bond: w by c ratio, aggregate roughness, and aggregate chemical composition. So we'll look at all the three factors one by one quickly. So what is the effect of w by c ratio? Higher w by c ratio means weaker bond strength. Why? Because as the w by c ratio increases, there is increase in capillary porosity. Okay, and there is increase in porosity at the ITZ also, which weakens the bond. As w by c ratio increases, the CSH formation is lower. Okay, less hydration product is available at the bond aggregate at the paste aggregate interface, so the binding between cement paste and aggregate is weaker. There is higher bleeding, so water may accumulate at the aggregate surface because there is more water, and there is an interface where there is wall effect happening. Okay, which can lead to a weaker layer between paste and aggregate. And there is more micro crack because higher is the water content, there are more chances that due to evaporation of that water, shrinkage crack can grow at the ITZ, which can lower the strength of the paste aggregate bond. Okay, so this is the effect of w by c ratio. Then what is the effect of aggregate surface roughness? So smooth aggregates, they try to weaken the bond because they have lower mechanical interlock with the cement paste, and they have a higher likelihood of ITZ failure. Okay, so in smooth aggregate surface, the crack propagation is simple because there is no hindrance to the crack propagation path. Okay, so that's why there is easy stress concentration at these surfaces are higher. Okay, so they are likely to have higher ITZ failure. And also, since the surface is smooth, the bonding with cement paste is also poor because of poor adhesion. There is no mechanical interlock between the aggregates also. However, in rough aggregates, there is better mechanical interlock and reduced micro cracking at the ITZ because it makes the crack propagation path more tortuous and more energy consuming. Okay, which can delay the crack at the paste aggregate bond. Then what is the effect of chemical composition of aggregates? So the inert aggregates, okay, they have moderate bond, they don't react with the cement paste, so bond strength at this at the paste aggregates, it is mainly due to the mechanical interlocking. Okay, however, if we talk about reactive aggregates, okay, they have stronger bond because they can undergo chemical reaction with cement paste. Like CaCO3 in aggregate, it can react with CSH to form some additional binding phases. Okay, due to this reaction, they have more adhesion with the cement paste, which increases the strength of the ITZ also. However, such aggregates are not recommended because they can show some harmful durability effects also later on. And harmful reactions like alkali Seika reaction, if it occurs, it can weaken the bond. Why? Because it is expansive in nature. Okay, and it can cause cracking in aggregate. Okay, so the chemical composition of aggregate can also have an influence on the paste aggregate bond. So this slide just summarizes the effect of aggregate quality and how it affects the paste aggregate bond strength and ultimately how it affects the strength of concrete. Okay, here it will be concrete. So aggregate qualities like surface roughness and chemical composition, in addition to the W by C ratio effect, it can affect the paste aggregate bond strength. Okay, along with the and this along with the paste strength can affect the strength of concrete. Okay, now there is one more question that will come up. Does the aggregate quality just influences the bond? Okay, the answer is no. Aggregate quality by themselves can also affect the strength of concrete. Okay, it is not that aggregate quality influences the interface strength and that interface strength influences the concrete strength. Aggregate quality by themselves also can influence the strength of concrete. How? So aggregate quality, as we said right now, rather than affecting the bond strength, can also directly influence the strength of concrete due to aggregate concentration, particle size, and the modulus of elasticity of aggregates. So all these things are core aggregate properties. They are not the properties which is dependent upon the interface. Okay, so if we see what is the effect of aggregate concentration, so a lower volume fraction. Okay, suppose we talk about a composition of concrete, okay, in which we have aggregates in the range of 50 to 70%. Okay, so what if my aggregates are lower than 50%? So low aggregate fraction, it weakens the concrete. Why? Because there is higher paste content in concrete. So lower is the aggregate content, more will be the paste content. Okay, inside concrete, if more is the paste content, there are chances for more shrinkage and micro cracks inside concrete. There are chances of more porosity at the ITZ, which can weaken the concrete ultimately. Then the optimal aggregate content, that is in the range of 50 to 70%, okay, or we say 65 to 75%, it leads to strong concrete. Why? Because overall porosity is reduced, there is good transfer between aggregate and cement, which leads to stronger concrete. However, if I have aggregates more than 70%, then it also again weakens the concrete. How? Because there is insufficient paste. So if my aggregate proportion is higher, my cement paste proportional will go down. If my cement paste proportion goes down, then there is insufficient paste that is present inside my concrete to coat all the aggregates. Okay, that will lead to poor bonding at the ITZ. Higher risk of aggregate segregation can be there since the aggregates are not binded properly, and upon compaction they can segregate, and there is risk of improper compaction that can arise. Okay, so that's why we say we have an optimum range of aggregate. Below, if we go below, then again concrete can be weak, and if we go higher than 70 or 75%, again the concrete can become weak. Then aggregate size. So larger aggregate size has a mixed effect on concrete strength. Okay, if we have a larger aggregate size, it has lower surface area. Lower surface area will demand less cement paste. Okay, so this will reduce porosity, shrinkage, and micro cracks that exist at the ITZ, which can improve the strength. However, the larger aggregates, they can also allow stress concentration at ITZ, which can lead to more micro cracking. So due to less paste, as shrinkage reduces, the ITZ cracking can reduce, but higher stress concentration at ITZ, so larger aggregate, it will allow more easier ITZ propagation, crack propagation through ITZ. So that can lead to more micro cracking at ITZ. So okay, so higher larger aggregate has both type of effect, positive effect and negative effect. However, when we talk about smaller aggregates, they usually have higher strength. Why? Because there is more uniform distribution of aggregates, which leads to lesser aggregate micro cracking, and there is better packing density. So larger aggregates may show wall effect, due to which there are bigger pores at the interface, which can reduce the strength. However, in smaller aggregates, these wall effects things are not significant. So the porosity at the ITZ is lower, which can improve the strength. However, one disadvantage is smaller aggregates have more surface area, which will demand for higher paste. Okay, and this higher paste demand can lead to shrinkage at the interface. Okay, so in this way it can affect the strength also. Okay, so uh, so you can visualize these things in the figure. So like in the first figure, you can see there are four curves, okay, representing different cement content. So these are the cement content value of concrete. Okay, it is varying from 170 kg per meter cube to 390 kg per meter cube. Okay, on the x-axis we have maximum aggregate size, maximum size of aggregates, and on the y-axis we have the compressive strength. Okay, so initially you can see as the aggregate size increases, the strength is increasing because of lower surface area of aggregate, okay, which reduces shrinkage, porosity, and micro cracking. However, you can see after a certain size, as the aggregate size increases, the strength decreases because of micro cracking that is existing at the ITZ due to stress concentration. Okay, however, this effect is not significant in lower cement content. Why? Because at lower cement content, ITZ is already weak. Okay, because of less cement paste available to coat the aggregate surface. So eventually, the size of aggregate, it won't. The larger size of aggregate won't affect much. Okay, it is the cement paste content will originally, like, it will increase the strength for lower cement paste content. Okay, as aggregate size will increase. And in the second figure, you can see again the compressive strength versus W by C ratio for different aggregate size. Okay, so as the aggregate size decreases at a particular W by C ratio, the compressive strength is increasing. Okay, because of more uniform load distribution and better aggregate packing. Then what is the effect of modulus of elasticity of aggregate on strength? So low modulus aggregates, which are soft, low density and lightweight aggregate, they weaken the concrete because under loading, soft aggregate, they can deform more than cement paste, leading to micro cracking at the ITZ. So when we talk about weak aggregates, they can also deform under load, and if they deform, they will also contribute to cracking at the ITZ. Okay, which can lower the strength of concrete. And even if if ITZ is stronger than the aggregate, then the crack can propagate through aggregate also. So that's why it weakens the concrete. Okay, and when we talk about high modulus aggregates, they lead to strong concrete because the crack can't go through ITZ. It needs to follow a tortuous path at the aggregate cement paste interface to grow. Okay, and there is better stress transfer. Okay, because of lesser strain mismatch between cement paste and aggregate as the in high modulus of aggregates. Okay, so you can see here in ordinary concrete and in lightweight aggregate concrete, you can see at certain W by C ratio, the lightweight aggregate concrete has lower strength compared to ordinary concrete because it allows ITZ to easily grow and propagate throughout the concrete. Now, this diagram again summarizes the effect of aggregate quality on strength. So, apart from the surface roughness and chemical composition, which affects the paste aggregate bond, we have now direct factors. Okay, which are aggregate proportion, particle size, and modulus of elasticity. So, these proportions, they can directly influence the strength of concrete. Okay, in addition to the compaction effort, how well we have compacted the concrete. Okay, so this was the effect of cement paste, aggregate cement interface, and aggregate quality on the strength of concrete. Now, try to answer these simple question. And in the meantime, if you have any doubt regarding the discussion that we had right now, you can ask. Any doubt regarding any part that you have discussed right now? How aggregates are affecting the paste aggregate bond, how aggregates are directly influencing the concrete strength, and how cement paste also influences the concrete strength. If you have any doubt regarding any of these three discussion, you can ask. If not, try to answer the questions. If the modulus of elasticity is much lower than the cement paste, what is the likely failure mode in compression? Okay, so what will be the correct answer for this? Can anyone tell me the answer? Just few slides back we discussed about the modulus of elasticity of aggregate. Okay, so the correct answer is either A or B. Okay, so we have seen that if the aggregate has low modulus of elasticity, then if the aggregate is very weak, then instead of crack forming a IT propagating through the ITZ, it can pass through aggregate also. So failure can occur due to crushing of aggregates. Okay, or cracking at the ITZ also can occur because there is higher stress mismatch. Okay, MOE, if the MOE of aggregate and cement paste they differ a lot, then under the application of load, both cement paste and aggregate they will undergo different kinds of strain distribution that can lead to mismatch in their deformation capability under stress. Okay, which can lead to cracking at the ITZ. Okay. Question number 7. Which of the following statement is false about ITZ in concrete? So we have discussed ITZ is it is the interface between the aggregate and the cement paste. Now this question says which of the following sentence is incorrect about ITZ? Can anyone tell me the answer for question number 7? Yes, the correct answer is C. So we the higher W by C ratio it strengthens the ITZ. No, this is incorrect. So you have seen as the W by C ratio increases, the ITZ porosity increases. Why? Because there can be bleeding water that can accumulate at the ITZ surface, or there can be shrinkage issues due to water evaporation, which can increase the porosity. And as porosity increases, the strength decreases. Okay. Question number 8. Which of the following is not a reason why a high modulus aggregate enhances the concrete strength? So, among these four statements, one statement is incorrect regarding how high modulus of elasticity aggregates it enhances the concrete strength. So, can anyone tell me the answer for question number 8? Yes, the correct answer is C. Okay. Why? Because high modulus of aggregate they don't deform more, rather they deform less. Okay, and they enhance the concrete strength by reducing the ITZ micro cracking and by reducing the stress mismatch with the cement paste. Okay, so they allow better stress transfer occurring through concrete and it delays the cracking in concrete. Okay. Question number 9 now. Which combination of factors would likely result in strongest concrete mix? So there are different combinations that has been given based on W by C ratio, aggregate structure, and aggregate based on aggregate property and W by C ratio. I have framed four options with different combination. Which of these combination will result in the strongest concrete mixture based on compressive strength? Can you think which option will be correct? Just go through all the options. So such questions you can expect in the NPTEL exam. Okay, so this question, like options you see, it is not just judging one slide or one small discussion. This is combining different sessions discussion, like aggregate property and cement water to cement ratio, how both of them influences the strength. Both concepts are being merged into a single question. Okay, so such questions you can expect more to come ahead. Yeah, the correct answer is B. Okay, so lower W by C ratio, it reduces the porosity, which increases the strength. Rough aggregate texture will provide better mechanical interlock at the aggregate paste interface, which can increase the strength. And high modulus aggregate, it can resist deformation and it can reduce stress mismatch with the cement paste, and all these will contribute to higher strength. So you can see here three concepts have been used: the W by C ratio, which governs the cement paste strength; the aggregate texture, which governs the paste aggregate bond property; and the aggregate quality, which governs the aggregate property itself. And all these three affects the strength of concrete. Okay, so in one question itself, we have talked about three different concepts. Question number 10, it is a case study for you now. A reinforced concrete beam has been designed for high compressive strength, starts to show early ITZ failure. Okay, so I am a designer and I made a reinforced concrete beam for high compressive strength, suppose for M55 grade. However, I see there is early cracking at the ITZ and there is poor load transfer between aggregate and paste. Okay, so now I wanted higher strength, but I can see cracking occurring at a lower strength only. So I wanted 55 MPa grade, but when I tested this concrete for compressive strength, I got a strength of only 30 MPa. So I asked the consultant how he prepared the concrete, how what were the components that he used in the concrete. The consultant, he told that the mixture used a large smooth river gravel and a W by C ratio of 0.45. Okay, so based on the comment that I got from the consultant, can you tell me what is the probable cause of failure? Okay, why my 55 MPa concrete failed at 30 MPa? Yes, the correct answer is A. So the key things that you should have noted is the large smooth river gravel. Okay, so what happens there is, we due to the presence of smooth aggregate, the smooth aggregates, they reduce the bond strength with the cement paste, and this high W by C ratio. So 0.45 W by C ratio is quite high when we talk about high compressive strength concrete. So generally, when we talk about a concrete having strength of more than 50 MPa or 55 MPa, the W by C ratio required should be lower than zero point 0.4 or even 0.38 or 0.37, lower than 0.38 or 0.37. Okay, so large smooth aggregates, they reduce the bond strength, and high W by C ratio, it increases the ITZ porosity. Okay, both of these, it results to concrete prone to early cracking under loading. Okay, so such case study types of question also may come in the exam, where you need to think about multiple theories that has been taught during the course. Okay, so let's move ahead now. Now, it is not just the internal factors that affect the strength of concrete, but often, especially in case of laboratory measurements, the testing setup or the testing sample dimension and shape, and even the condition, can also influence the strength of concrete. And that's the reason why there are standard provisions that have been designed to for conducting compressive strength of concrete. And one such standard provision is the IS 45516 guideline for compressive strength of concrete. So this is an Indian standard. Okay, so if you see, there are different clause that are present in this guideline. So clause 2.8 of IS 516, it says that the test sample should be cubical in shape of size 150 mm, 15 centimeter, you can say it 150 mm. Okay, if the mean maximum part size of aggregate do not exceed 20 mm, then we can use 10 mm, 10 centimeter side cubes also. And the clause also says that cylindrical samples shall have length to diameter ratio of 2. So L by D ratio of cylinders should be 2. Okay, they shall be 15 centimeter in diameter and 30 centimeter in height. So this clause has given condition on the of shape and size of concrete, okay, to be tested. Okay, then clause 2.11 says that end of all cylindrical test specimens that are not plane within 0.05 mm shall be capped. So this again gives this clause talks about the condition of concrete, okay, prior to testing, okay, the presence of roughness on concrete surface. Then clause 5.3 and 5.5 says that the testing should be conducted at 7 days or 28 days. Specimens should be stored in water and then immediately tested after removal in water until while they are in wet condition, and loading shall be applied continuously at a rate of 140 kg per centimeter square per minute. So these three clause, you can see, they are giving condition on testing, okay, method, okay, and the sample condition during testing. Then clause 5.6.1, it says that equivalent cube strength of concrete shall be determined by multiplying the cylindrical strength by 5 by a factor of 5 by 4. So if we have tested a cylinder, if we want to convert the cylindrical strength into cube strength, we need to multiply a factor of 5 by 4. Okay, so this clause again, it's talk about the shape of concrete. Okay, so the things that are marked in red in this slide is the focus area. And what are they concerned with? They are concerned with the concrete sample size, they are concerned with the shape of concrete sample, the surface condition of concrete sample, the moisture inside concrete, and the loading rate while testing. Okay, so how these factors they are affecting the strength, and why clause has specified specific number for each of them, so that will look now in the ahead slide. Okay, so first we'll look at the effect of shape on the compressive strength. Okay, so this effect is generally known as the end platen effect. Okay, so generally, so suppose this is my concrete and this is my compression testing machine. So this is the top plate and this is the bottom plate, and then I'm applying a compressive load on concrete. Okay, so when we test a concrete for compressive strength in lab, there can be two shapes of concrete. Either there is a cube or there is a cylinder. Okay, so suppose we have a cube, okay, which is getting compressed between two plates of a compression testing machine. So what happens when this steel plate, it will come in contact with the concrete, okay, it will try to push the concrete outward, okay, because it is trying to squeeze the concrete. Okay, now, however, there is friction which will be present between the steel plate and the concrete, which will try to oppose this outward movement and it will try to push the concrete inward. Okay, so you can see that this effect is there at the interface. However, if we will move away from the interface, we'll see this friction effect will decrease and there will be a stress plane there will be a critical stress envelope that will be developed, okay, like this. Okay, so here my frictional force was maximum. Okay, as I will move away from the plate, the frictional force will decrease. So this external force that was applied due to plate movement, it will start to dominate. Now this effect which is occurring at the interface between the end plate and the concrete, this is known as end platen effect. Okay, and theory says that this end platen effects, it lasts up till 0.866 d. Okay, where d is the depth of my concrete. So suppose this is my depth of my concrete d, so up till 0.866 d, this frictional effect will be there. Okay, so this effect that you can see here, it will diminish at a depth of 0.866 d. Okay, however, when we talk about a cylinder, suppose we talk about a 10 side cylinder. Okay, so my mid portion it has is at 0.5d, okay, which is lower than 0.866. So that's why if we see a concrete cube tested in compression, so there won't be a fracture zone like this which will be formed. Okay, there will be a fraction zone like this. Okay, so at the middle also there is some frictional resistance which is offered to the external, to the um, outward force. Okay, that is there. Okay, so that's why we say concrete has higher strength. However, instead of concrete, if we have cylinder, so suppose I have a cylinder of depth 300 so my d by 2 will be higher than uh, 0.866d. Okay, so in such case there will be a zone that will be formed. Suppose my depth is 2d, okay, and this diameter is d. Okay, so in such case what will happen, this depth is higher than the 0.866d factor. Okay, so what will happen, there will be a zone in the middle where there is no frictional effect, there is just external outward force that is acting due to the compression load. Okay, so this will become a weaker plane for failure, and thus the load that we find when we test a cylindrical sample in compression is lower than the load that we find when we test a cube in compression. And that's why we have this clause 5.651 which says that whatever strength we got for cube, okay, for cylinder, if we want to convert it into cube, then we need to multiply a factor of 5 by 4, that is 1.25 times. Okay, so this is known as end platen effect, and this is the effect of shape of concrete on the compressive strength. Now after shape we have the in shape again, within a cylinder and within a cube, more effects can come up. Okay, so larger specimen, it is shows, they show lower strength compared to smaller ones. Why? Because in larger concrete there can be higher probabilities of defects like voids, micro cracks, and heterogeneity, which can lead to early failure. And that's why we say that as the size of concrete sample increases, the strength decreases, and you can see this in this table. Okay, so if for a 150 or a 100 cube, if my strength is 1, if I reduce the size to 70 my strength is increasing by 10%, and if I increase the size to 200 or 300 my size strength is decreasing by 5% and 10%. Okay, so this is the effect of shape of concrete cube on the strength. Then as the h by d ratio of cylinder increases, the strength decreases. By because there is buckling effect. So as the height increases, so this load that is acting in compression, it will generate buckling moment on the concrete cylinder, which can lead to early failure of cylinder. Okay, so this is known as slenderness effect, okay, which will cause buckling in concrete, which can reduce the strength of concrete. Okay, so that's why you can see in this slide, in this table, as h by d ratio, we saw as we decrease the h by d ratio, the strength is increasing. Okay, we need to apply a correction factor. Okay, so generally when we report strength, we report it for h by d ratio of 2. Okay, if we have a h by d ratio of 1, we have overestimated the strength. Okay, so we apply a correction factor of 0.89 to the strength that we got for h by d ratio 1 to convert it into h by d ratio of 2. Okay, and this correction factors are, they are provided for different, provided by different standards for different h by d ratio. So if h by d ratio is less than 2, the strength is overestimated, so we need to reduce the strength. And if by h by d ratio is greater than 2, then due to buckling the strength has been underestimated, so we need to increase the strength by suitable correction factor. Then we have loading rate. So loading rate simply means the rate at which we are applying the load on concrete. Okay, when it is tested in compression in a compression testing machine. So generally code says that the loading rate should be 14 Newton per millimeter square per minute. Okay. However, if you have a larger loading rate, what will happen? It will increase the compressive strength. Why? Because the crack that are forming inside concrete, they will have lesser time to grow, connect, and propagate. Okay, so we, the crack propagation won't be idle, so it will increase the strength of concrete. The cracks won't be allowed to connect to each other, and in such cases at higher loading rate we'll see brittle happening. Any doubts? Okay, so when we increase the loading rate, the crack propagation is not idle. Okay, it won't allow the cracks to grow and connect, and thus we will have brittle failure in concrete. However, if we have a lower loading rate, then what will happen? We will have a lower compressive strength value, because micro cracks, they will grow and connect more easily, and it will cause failure in concrete before eventual failure. Okay, so that's why failure is more gradual, and it represents long term behavior. Okay, however, as per standard, we need to test with 14 newton per mm square per minute rate. Okay, for getting a standard value which will be acceptable everywhere. Then next is the effect of moisture content in concrete. So we have seen few slides back that code says that samples stored in water shall be tested immediately after removal from water until they are in wet condition. So why is that so? So in saturated concrete, what happens? All the pores are filled with water. Okay, now since water is incompressible in nature, when we applied the load on concrete, the pore water, it won't squeeze out instantaneously. And since pore water is not squeezing out from concrete, it will generate some pressure inside the concrete. Okay, which will try to resist the load, and which will also cause cracking inside the concrete. And thus the saturated concrete, they have lower strength compared to dry concrete. Okay, so due to presence of water inside concrete, which is incompressible in nature, the micro cracks, they will initiate early inside the concrete, and they will propagate early, which will cause to premature failure and lower strength inside concrete. But why then code says to use saturated concrete instead of dry concrete? So that we have get a compressive strength value on a safer side. Okay, okay, so when we test a saturated concrete, we get a lower strength. So if we are getting lower strength, we are getting a concrete on the safer side. Okay, so that's why code says to test concrete just immediately after removal from water. And in this table, you can see the correction also. A moist concrete, it is at suppose at 1.00 mark. So dry concrete will have a strength of about 1.05 times more than the moist concrete. So it is 5% more. Uh, 5% more than the moist concrete. Then finally, we have in case of cylinders, we have talked about capping. So you saw in this clause 2.11, which says that all cylindrical samples that are not plain should be capped. Okay, so the capping material, why we do capping? So capping is done to ensure that there is a smooth surface available under loading. So when we apply load, so this surface should be smooth. If it is not smooth, then what will happen? There will be crushing of concrete at the surface itself, which can lead to failure of concrete. Okay, this machine, once this concrete will crush at the surface, will assume that the failure has occurred and the testing will stop. If there is a smooth surface, then there will be proper stress transfer that will occur from the machine to the concrete bulk. Okay, and for making a concrete surface smooth, we use capping material. Now, the property of a capping material can also significantly affect the strength of concrete based on the stiffness, friction, and the stress distribution. So there are different types of capping materials that are used. There is alumina cement, gypsum plaster, there is sulfur with filler, there is sulfur, there is plaster of Paris, there is POP with OPC. All these types of capping materials are there available in market, which are used to smooth level a cylindrical surface. In a weak concrete, capping material, it may not influence much. Okay, but for a strong concrete, the type of capping material which we are choosing can have a major role in the strength of concrete. How? So if we take a small, soft and a weak material for capping, what will happen under the action of compression load? It will undergo lateral expansion. Okay, so if we have this concrete column, the cylinder, and this is a capping material, when we apply load on the concrete, this capping material, it will undergo lateral expansion. Okay, and as it will undergo lateral expansion, it will decrease the confinement effect that the interface provides. Okay, so we know that there is a frictional effect at the interface which resists the external outward force that is generated due to compression. If it will undergo lateral expansion, this confinement effect due to friction, it will decrease. Okay, so crack will grow more rapidly through concrete, and thus failure will occur at a lower load. So that's why generally we prefer a capping material of higher strength, and most commonly we use alumina cement for capping, okay, in laboratories. Okay, so this was the effect of different parameters. We talked about sample shape, the end platen effect. We talk about the dimension of sample, smaller size sample, a larger size sample, how they affect the compressive strength. We talked about the loading rate, how it affects the compressive strength, the moisture state in concrete, how it affects the compressive strength, and the capping material property, how it affects the compressive strength. Now, based on these external parameters, just try to answer the questions, and in the meantime, if you have any doubt, you can ask. So, what will be the answer for question number 11? Can anyone tell me? Which capping material is most accurate for high strength concrete? So, I have just shown you the list in the last slide. So, based on this list, we saw that for high strength concrete, capping material is important. It can significantly influence the strength. Okay, so what capping material you will recommend for high strength concrete and why? Can anyone tell me the answer for this question? If you have any doubt regarding any concept, you can ask freely. Any guesses? So there are three options which are saying about different capping material, and fourth option is saying about grinding of sample. Okay, I will tell you the answer for this question. The correct answer is D. So it is better to grind the sample and make the surface smooth rather than applying any capping material. Why? Because any form of capping material that we apply on the concrete surface, it will decrease the lateral confinement effect by some margin. Okay, so better to make the surface smooth naturally by grinding rather than using a capping material. However, grinding a sample surface is not always possible because grinding it can cause some internal damage to concrete's microstructure also because of vibration that we are applying to the concrete. So that's why people generally don't prefer grinding, they prefer capping. However, if there are small irregularities on the surface, then it is better to go with grinding rather than capping. Okay. Question number 12. So it is a numerical question now. So a concrete cylinder of diameter 150 mm and 300 mm height is tested for compression using three different capping materials. Okay, so sulfur capping gave me a strength of 42 MPa, rubber pad capping gave me a strength of 45 MPa, and gypsum plaster capping gave me a strength of 38 MPa. So can anyone tell me what is the percentage variation in strength that we have observed here? So it is more like a statistical question rather than a uh, question related with concrete strength. Can any one of you do the calculation? What is the percentage variation in strength that you are observing here? Does anyone know how we calculate percentage variation? Okay, I will tell you how we calculate percentage variation. So percentage variation, it is basically maximum value minus minimum value times 100 divided by minimum value. Okay, now just do the calculation for me. You have all the three values given. So what is the maximum and what is the minimum value, you know? So what will be the percentage variation then? So it is 45 minus 38 times 100 divided by 38. So this will come out to be 18.4%. Okay, so this much percentage variation is existing due to different capping materials that has been used on the same quality of concrete. Okay, so that's why what capping material we are using becomes very important. Now there are two more questions. So both are a case study question. So question number 13 says that a research team is studying the effect of specimen size on compressive strength. They have tested two concrete cubes of different size but from the same batch. Cube 1 has a size of 150 mm sides, compressive strength was 45 MPa, and cube 2 has a concrete of 300 mm side and it showed 40 MPa strength. Why there is lower strength in larger cube? Okay, what is the reason? Can anyone tell me? The concrete quality that is there in both the cubes are the same. The size is the different, which is causing change in the strength of the cubes. What can be the reason? Can anyone tell me the answer so that we can move ahead quickly? It's a very simple question. Just try to think. There is a very clear answer that is there in the options. Where the correct answer will be A, because in larger specimen size there are more chances of more interfacial defects and micro cracks that can exist. So that's why a larger concrete cube showed a lower strength compared to a smaller concrete cube. Okay. Now this question number 14 you can attempt on your own because this question is based on curing of concrete that we saw in the last live session. So this question says that there are three samples. Concrete is same in all the three samples, or however curing is different in all the three. Okay, first sample is moist cured at 95% RH for 28 days. Second sample is cured in open air. Okay, and third sample is cured in water, but after oven and but it was oven tried before testing. Okay, so what will be the strength order in this concrete based on the hydration and the moisture effect? So you can see here there are two concepts that has been mixed. One is curing of concrete and second one is the moisture effect, moisture present in concrete. Okay, so I will just tell you the answer quickly so that we can move ahead to the next concept. So the answer will be C will be greater than A will be greater than B. because in C, curing is done in water, but it was oven dried. So we have seen that a dry concrete has more strength than a moist concrete, and A is greater than B because in A it was moist cured for 20 days while B was cured in open air. And since it is cured in open air, there will be evaporation loss from concrete, which will reduce the strength of concrete as moisture available for hydration will be lower compared to in the first case where there was enough moisture available for hydration inside concrete. Okay, so that's why B will have the lowest strength and C will have a higher strength than A. And A is my ideal condition in which code says to do the testing. Okay, I hope these concepts were clear to everyone. If not, you can always use the chat box or unmute and speak to clarify anything if there is any lack of clarity anyway. Okay. Now, after compressive strength, the last part of our discussion today is the tensile strength of concrete. So we know concrete is a brittle material. It is strong in compression but weak in tension. Okay. But still, we talk about tensile strength of concrete because it governs the crack formation and propagation. Okay, it affects the structural behavior under flexure and shear, and it determines the bond strength with the reinforcement and reinforced concrete structure. Okay, due to these three reasons, although we know compressive strength is lower, we still talk about compressive. Although we know tensile strength is lower, we still talk about tensile strength of concrete. And also, since concrete is weak in tension, and that's why we use steel reinforcement inside concrete. Why? Because steel is strong in tension, it is thermally compatible with concrete, and both concrete and steel can work as a single unit. Okay, concrete can protect steel from corrosion, while steel is protects concrete from tension load. Okay, so that's why commonly when you see structures outside, you will see there are reinforced concrete structure. Okay, now if we look at the quantitative data, the direct tensile strength of concrete. So this is my concrete cube. I am applying a compression load. And on the same concrete cube, if I apply a tension load, so this direct tensile strength of concrete, it is only 8 to 15 times the compressive strength of concrete. And we can generally estimate this using this relationship. So Ft is the tensile stress and Fc is the compressive strength. So if we know the compressive strength is 55 MPa, then using this formula we can calculate the tensile strength of concrete. Okay, so now this is direct tensile strength of concrete. But since concrete is brittle in nature, it is very difficult to test a concrete like this under direct tension. Okay, so that's why there are several indirect methods that are used to determine the tensile strength of concrete. And those two methods are split tensile strength as per IS 5186 guideline and flexural testing as per IS 516 guideline. Okay, so we'll look quickly into both the testing. Okay, so first is the split tensile strength. So in this, what we do, we take a concrete cylinder and we load the concrete cylinder in compression testing machine. Okay, so when we load the concrete cylinder in compression testing machine, what happens, since the surface area which is in contact with the plates that is very small, so the frictional effect at the surface is very small. So this entire concrete, it is under tensile stress that is generated due to the compression action of the plate. Okay, this end platen defect, it is very small. Okay, since it is loaded diametrically. Okay, so what happens under this loading, concrete will crack from the middle. Okay, and the failure will be tensile failure because of this tensile stresses that is acting. Okay, it is splitting the concrete apart. Okay, so compression failure creates a tensile stress along the vertical diameter. Okay, and which leads to splitting of concrete, and based on the maximum load under compression, we can calculate the split tensile strength of concrete using this formula, 2 pu upon pi dl. Okay, so this is split tensile strength. Then there is flexure testing that is done on concrete beams. Okay, so a prismatic concrete beam, it is placed under either 3-point loading or 4-point loading. Okay, so these two bottom uh, supports these are the supports that we provide on the beam, and these roller, it is through which load is exerted on concrete. So in 3 point loading, there is through this roller single point there is load applied. So my bending moment diagram will be something like this. While in 4 point loading, at both these loads, rollers, the load is applied. So my bending moment diagram is like this. So there is a central portion in which there is maximum bending occurring inside the concrete, while in 3 point loading there is one critical point at which maximum bending stress is acting. So when you see failure, it will be passing through this point. While in 4 point loading, failure plane can exist anywhere between this central portion. Okay, this portion. Okay, so beam experiences tensile stress at the bottom fiber, and it fails due to when tensile strength exceeds the tensile stress exceeds the tensile strength of concrete. So we have seen in design of RC, there is neutral zone. Above neutral zone, the concrete is in compression. Below neutral zone, the concrete is in tension. So when we apply load, slowly as the load increases, the bending moment that is exerted at the bottom, below the neutral axis, also increases, and slowly it will generate the bending stress which will exceed the strength of concrete in tension, and it will cause failure of concrete. Okay, so based on the amount of load that is exerted on this roller, we can calculate the modulus of rupture of concrete, okay, or flexural strength of concrete. So under 3 point loading, we have this formula 3pl upon 2bd square, while in 4 point loading we have this formula pl upon bd square to calculate the strength of concrete. Okay, so these images these are like some of my samples that I have tested in lab for flexural strength. Okay, so this concrete you can see here, it is a concrete without any fibers inside. So under 4 point loading, you can see these two are the points through which the load was applied, and these are the supports. Okay, so when load is applied, you can see a crack growing in the middle between the two rollers. Okay, so this portion was where maximum bending was existing. So crack happened, it started from here and it went till the top. Okay, so this kind of failure you will see under bending. And while if the concrete has some fibers inside, so what will happen, these fibers will, they will try to bridge the crack. So you see here the crack opening was thicker. Okay, the crack width was thicker, while here the crack width is not that thick, because although the crack has formed because of concrete failure in tension, the crack is not growing because there is fiber which is holding the crack together. So once the fiber will fade, the crack will open up further. Okay, so that is the positive use of fibers in concrete. They resist the crack from growing. Okay, and these are the this setup is for 4 point loading for flexural strength. Okay, in bending. Now, based on your understanding about tensile strength, just answer these two questions. So these two are all case study questions. Okay, based on them, based on the case study, just give me the answer. So the first question says that a high performance concrete was tested for both flexure strength and split tensile strength. I recorded a flexural strength of 7 MPa and split tensile strength of 4 MPa. Why split tensile strength was lower than flexural strength? Can anyone tell me? So you know the both the methods. So in flexural strength, we do testing like this in 3 point loading or 4 point loading. Okay, and in split tensile strength, we have a frame like this. So why my split tensile strength is lower than the flexural strength? Can anyone tell me the answer? Okay, correct answer will be A. Flexural strength will be always higher due to stress distribution. So if you see both the figures, okay, so flexural strength is typically higher than split tensile strength because the way in which the stress is distributed. Okay, so in flexural testing, what happens, there is a neutral axis. Okay, above neutral axis the concrete is in compression, below neutral axis the concrete is in tension. Okay, so failure is governed by the tensile cracking that is occurring below neutral axis. Okay, above neutral axis it is not under any tension force. However, if you see split tensile strength, okay, so and across the stress is uniformly applied across the diameter. Okay, and this tensile strength acting from top to bottom. Okay, it is not like just below neutral axis there is tensile loading. The tensile loading is uniform across the diameter, so that's why it has a lower strength. Fluid tensile strength is lower compared to flexural strength. Okay, the way in which stress distribution is occurring. Then question number 16. There are two cylinders of same mixture design and they were tested for split tensile strength. Cylinder A, which is of larger size, it gave a split tensile strength value of 3.8 MPa. So now I have a cylinder B which has smaller size. So this is my cylinder A and this is my cylinder B. It has a lower diameter and lower height, and this had a higher diameter and larger height. Okay, so if I know the split tensile strength value of this sample, what will be the split tensile strength value of my smaller sample? Will it be higher or will it be lower? So whether it will be higher than 3.8 MP or lower than 3.8 MP? Can anyone tell me? This question again is like these questions, they both are again using multiple theories that we have discussed across the discussion today. The effect of size, the effect of testing method. Since we don't have much time left in the session, I will tell you the answer. The correct answer is B. So, as we talked for concrete cubes, larger is the cube size, there are more chances for internal cracks and flaws to be present inside the concrete. So, strength will be lower. Okay, so since I have a cylinder A has a larger size, cylinder B has a smaller size than cylinder A, then it may show a split tensile strength value of more than 3.8 MPa because of lower size effect. Okay, so this was all for today's session. We talked about strength of concrete. We discussed different theories which says why concrete is strong in compression and weak in tension, the CSH theory and the crack theory. Then we discussed how micro crack, pore volume, cement paste bond, aggregate paste bond, aggregate property, they affect the compressive strength of concrete. We discussed how testing setup can influence the compressive strength of concrete based on the shape of concrete, the size of concrete, the loading rate, the moisture content in concrete, and the capping material used in cylindrical concrete. Okay, how they affect the compressive strength value. And finally, we discussed about tensile strength of concrete and how tensile strength of concrete is determined. Because concrete is weak in tension, we can't do a direct tension test on concrete because it is brittle in nature. So we have alternate methods which are split tensile strength and flexural strength. Okay, so this is all for today's session. Thank you. Now if anyone has any doubt left